welcome everyone to the next webinar in our year-long DDS Foundation series of webinars, celebrating 20 years of DDS innovation. I want to thank you for joining us today. My name is Laura Clark. I'm VP of Communications for the DDS Foundation. As we continue to celebrate the 20th anniversary of the DDS standard, today's webinar is entitled DDS, the FAQs About QoS. Please feel free to ask questions and we'll get to them at the end of the presentation. It's my pleasure to welcome today's speaker, Justin Wilson. Justin has a PhD in computer science from Washington University in St. Louis. For the past 5 years, he has worked at the intersection of IoT and DDS, which utilizes DDS, RTPS, security, and X-types. He is currently the acting director of the OpenDDS Foundation and an executive member of the DDS Foundation. And now I'll turn it over to Justin.
Thanks, Laura. As you can see from the title, we're today talking about QoS. And to kind of set the table for what we're going to talk about, first I'll give a very brief summary of QoS, what it is, why it's important. I'll then give a very brief introduction to DDS. I need to introduce some concepts so that the rest of the talk makes sense. I imagine that most of you are already going to be familiar with this, so I'll try to keep it very brief. Then we'll talk a little bit about QoS fundamentals, how you work with it, and some of the ideas that apply to every QoS or most of the QoSs. Then we'll actually take a look at the 22 QoS policies in the DDS spec. We are going to get a little technical, but not too technical. And my hope is really to give you an idea of the breadth of what the QoSs in the DDS spec encompass. So what they do, when to use them, and then some gotchas that you can experience when working with them. Finally, then I'll just offer some very brief conclusions, and then we'll answer questions from the audience if there are any. So let's get started. So QoS or QoS, I'll say it QoS, it's a little bit easier for me, stands for quality of service. So QoS policies describe what behavior is expected rather than how it is accomplished in a DDS system. This is very important. By separating those two things, it allows us to reuse behaviors that are very common or very useful. So for example, let's say the design of a distributed system says that the communications between A and B should be reliable. Every message that A sends should be received by B. So if you're using DDS, the code would then configure A and B for reliable communication. And then the middleware itself, or the service, would then enforce reliable communication between A and B using whatever mechanism was implemented. So this separation of design time, implementation, and runtime concerns allows that idea of reliability to be reused. And it reduces the amount of code that needs to be written by the person implementing. And it also gives a vocabulary to the designer to talk about different aspects of their system and how they want it to perform or behave. There are DDS QoS policies for a number of different areas. First of all, attaching metadata to entities, which is important for kind of configuration, monitoring, things of that nature. Controlling which entities match and communicate. That's an idea for managing complexity and scaling. Accessing historical data is important for applications that need some kind of cache of data so that they can make decisions, etc. Establishing order and coherency in a sequence or group of changes. I hesitate to use the word database and transaction here, but that's what it's trending towards in the sense that you can deliver a set of changes by preserving order and grouping into a remote, and they can see exactly what happened at the origin of those changes. There's capabilities for working with time-sensitive data, managing redundancy, which is important for fault tolerance and high availability, controlling reliability and the priority of communications, and then finally managing the resources that applications would use. So a very brief overview of DDS. So DDS starts with the concept of a domain, which is a general container of applications. Each domain is separate from the other domains, and if you want two domains to communicate, you have to write a special application that joins both domains. So domain is a collection of participants. A participant then is a collection of publishers, topics, and subscribers. Publisher is a collection of data writers, and a subscriber is a collection of data readers. Each data writer is associated with one of the topics that was created in the participant, and a data reader similarly is associated with exactly one of those topics. So these, the things covered by that brace there from participant down, are called entities, and each one of these have an associated QoS policy. The way DDS works is we start by defining a topic data type. In this case, we'll call it telemetry. For satellites, we can give these things a key, which is going to identify our satellite, and then we'll have some kind of data payload that we wish to communicate. So the value of this topic data type is called a sample. I'll be using the word sample very often in this talk. And then samples with the same key belong to the same instance. So we can think of all of the samples that have the same satellite key value belong to that satellite, and they could represent the changes for that satellite over time. So we may have multiple data writers all on the telemetry topic, perhaps corresponding to different satellites or maybe the same satellite. Then we'll have various data readers on that topic that wish to consume data about the satellite. So the data writers will write telemetry samples, and then the data readers will either read or take telemetry samples. The general process then is they will go through a process called discovery, where they will find each other. They will then match if they have a compatible QoS, which we'll talk about in just a moment. And then finally, if all of that works, they will then start communicating. So QoS is really a part of all of these processes. It controls discovery, it controls matching, and then it also governs how the communication takes place. Not what is communicated, but how. So some fundamentals. The DDS spec section 223 defines the 22 individual QoS policies. The writers wasted a lot of ink on it because it's so important. The QoS for DDS entity, which is again is a participant, topic, publisher, subscriber, data writer, or data reader, consists of one or more of the QoS policies. So not every policy applies to every entity. It's going to be some subset that's relevant. You specify the QoS when it's created, and some of the QoSs can be changed dynamically after the entity has been created. So the spec defines defaults, which are probably not what you want. You probably want to tweak them in one way or the other to make sense for your application. And then there's factories that can also provide defaults. So perhaps if you know you're always going to be reliable, you can change the default one time and then not have to set it for every entity you create. So a data reader and data writer must have compatible QoS to exchange data. So for some QoS policies, the QoS that's offered by a data writer must be, we say, greater than or equal to the QoS requested by the data reader. So for example, if I have a reliable data writer and an unreliable data reader, that works. The data writer is providing a stronger guarantee than the data reader needs. However, vice versa doesn't work. If I have an unreliable writer and a reliable reader, then the reliable reader's expectation is never going to be met by that unreliable writer. So those won't match and they won't exchange data. The application can receive an event if there's something out there that's on the same topic, but the QoS is incompatible. And then you can also find the QoS for discovered entities using the built-in topics, which is another talk in and of itself. So let's get into the individual QoS policies. The user data, topic data, and group data QoS policies are really binary blobs that you can attach to various entities, and you can access these via the built-in topics. So the way these are used is really to convey application-specific data, such as IDs, configuration, serial numbers, et cetera, et cetera. And one of my favorite things to do is to use some kind of extensible encoding for these, like JSON or XML, so that an application can continue to expand its use of the user data or group data or topic data as it evolves over time. And one of the gotchas is that depending on security in your implementation, this data may be sent in the clear. You should not put sensitive data in these things unless you're absolutely sure that security is going to take care of that for you. The partition QoS is a list of strings and or patterns, and the data reader and data writer can match if a partition in one matches a partition in the other. So Partitions are checked by security if you're using security, and I could get into that detail later. I don't necessarily want to right now. But the use of partition is to logically divide a domain into smaller groups and simplify application logic. So for example, let's say I'm running a plant, and that plant has a sensor and a controller. So I have a sensor for my first plant, plant 1, and it's feeding data to my controller for plant 1. So I might put those in the plant 1 partition. And then I spin up another plant, plant 2. Same application, same sensor, same controller, but this time they're in plant 2 and they're in plant 2. So the sensor readings from plant 1 won't go to the controller of plant 2, and the sensor from plant 2 won't go to the controller for plant 1 because they don't have a common partition. However, I can do something interesting here and say I want to collect data from all the sensors because I want to build a dashboard or something from my plants. So what I can do is I can create a monitor application that is in the plant star partition. I can use a wildcard there to cover all the plants that I would ever make. So then I can collect data from the sensor for plant 1 and the sensor for plant 2 to build a dashboard that covers everything. So partitions are really flexible, and they're kind of a Swiss Army knife for handling complexity and scaling. So one of the gotchas here is that there's no feedback if your partitions aren't correct. There's nothing that says it was incompatible QoS. It's just they never matched. So you never quite know when it's not working, perhaps why it is. But if it isn't working, partitions are one of the things to go look at to make sure that they're correct. Historical data. So the history QoS instructs the service to keep old samples for an instance. So if you need to compute like a trend or show some kind of historical data, a moving average, etc., you would use the history QoS to keep some of those samples that have already been produced, keep them around so that you can display them, process them, etc. There's really two flavors here. One, it can be keep last with a depth, or keep all. So keep all obviously can read resource leaks, so you need to be very careful if you're using that. There's additional QoS for historical data. The next one is durability QoS, which instructs services to make samples available for late joining readers. So for example, you may have a writer that's always online producing data, and you may have a reader that periodically comes up, gets some data, and then shuts down. Well, all of the data that the writer has already produced may be useful to that reader that comes late and then leaves, or just needs to catch up. Or perhaps you have a network problem, and then the reader needs to catch up. There's a variety of reasons why you'd want to do this. In any case, there's 4 levels. There's volatile, which means the writer makes no samples available and the reader doesn't demand any. Transient local, the writer will make samples available and the reader wants them. Transient, which is like transient local, except that it answers from memory and even can answer after the writer goes away. And persistent is like transient, except you're actually going from permanent storage instead of just memory. The durability service QoS really governs how samples are managed for the transient and the persistent QoS setting for durability. So it consists of 3 things: a cleanup delay, because you can't hold on to everything forever. So you have to specify a delay that will eventually clean up those samples. A history policy, which is very much like the history policy for the volatile and transient local. And then a resource limits policy, which also facilitates cleaning up data that shouldn't necessarily be there, or keeping it into a finite set. So one of the issues with transient persistent is that they're optional, so not all implementations have them. And then they're also not interoperable. The interoperable spec, RTPS, doesn't cover how that's used. So most applications will stick to volatile and transient local. So for a couple examples, you could have a DataWriter with keep last 5, transient local, DataReader, keep last 10, and transient local. When the reader starts up, it's going to get 5 samples from the writer. It'll then get the next 5. Then its history is full. So then every sample that it gets afterward will replace. We can replace the oldest sample. We can switch those around. So the DataWriter has 10 and the DataReader has 5. The reader at this point gets 5 at startup, and then every sample is going to replace the old one. So we can ask questions like, does DataReader keep last 10 volatile make sense? Yes, absolutely. That just means that it doesn't necessarily care about data that's already been written, but once it has 10 samples, it's happy. And then we could ask, well, does DataWriter keep last 10 volatile make sense? Well, probably not, because 9 of those samples, and even actually all 10, are not necessarily ever going to go anywhere after they've been written. So not that you can't do it, it's just you might not be doing what you think you're doing is one of the issues when using QoS. Order and coherency is the next one. So the presentation QoS, which is very complex, allows changes to be grouped and ordered. So if you enable coherent access, then changes between these two method calls, begin coherent change and incoherent change, are presented as a group to the reader. So if ordered access is enabled, then the order of changes is also preserved. So those two things are orthogonal. One is just the grouping to say, all of this stuff happened on the writer, package it as a unit, and then present it to the reader once that you have everything in the package. The sequence is, the ordered access is slightly different, and it says, I just want you to trace the order. So you can present it piecemeal as you get it, but overall you have to keep the order. You can enable both of them, in which case you get them as units defined by the application and the order is correct or available on the reader side. So this can be applied to instance level, topic level, applying all the samples in a DataWriter or DataReader, or a group level at the publisher and subscriber level, which makes it kind of more transactional. So you can have changes across topics, across data writers that are all grouped and sequenced to where they can be, that sequence and that grouping can be communicated to the reader side. So you would use presentation when either the sequence of operations is really important to preserve so that the reader knows what happened on the writer and in the order it happened, or the whole unit must be delivered, kind of like an atomic thing where all of these changes need to be visible on the reader at the same time. So one of the gotchas here is that group is optional, so not implementation support it. And the other gotcha is that the logic that reads the samples must be correct to take advantage of order and coherency. So the DataReader API is very, it's not complex, but there's a lot to it. And you need to avoid using certain pieces of it if you're going to actually enable this feature and take advantage of it. Otherwise, the service is going to not maybe perform as efficiently as it could because it has to keep track of all these bookkeeping details. So you have to be judicious with your use of presentation, and you have to make sure that your reader is ready for it. Time concerns. So DDS is very big in the real time, and I'll let you define what real time is for you, community. And there's a couple of QoSs useful for that. The first is lifespan, which sets an expiration date for a sample that's written. So the current time is computed and then extended by some amount into the future. And once that time elapses, it's purged from the writer and reader. So it's a very useful way of, if you have transient data, to allow it to get cleaned up and purged from the system in an orderly fashion without managing it manually. The next one is the deadline QoS, which defines a period where the data writer promises to write a sample or a deadline missed event is triggered. So this doesn't, the middleware is not enforcing, like it's not requiring that the writer write a sample, but it is going to report when it doesn't. So you use that for monitoring, and that we're going to see this come into play when we talk about the ownership QoS in just a moment. And then the final kind of time concern is called time-based filter. And what this does is it allows a reader to express that I'm only interested in samples when they are so far apart in time. So if you have something writing at 100 hertz, but you're really only interested in 10 hertz, then you can specify your time-based filter, and that allows the publisher to perhaps downsample and only convey the necessary samples to satisfy that particular reader, perhaps saving some processing and network bandwidth in the meantime. So you really shouldn't use this with reliability, which we'll talk about later, because this is a QoS policy that's encouraging you to drop samples, whereas reliability is a QoS policy which says you can't drop samples. So These are lifespan, deadline, and time-based filter are 3 QoS policies that allow applications where timing is very important to make decisions and automatically manage things. The next topic is redundancy. So multiple data writers can write the same instance. If we go back to our satellite example, we may have multiple data writers for redundancy purposes producing data for that same satellite. So this is used for fault tolerance and high availability scenarios. So the ownership QoS is used in this area, and it has one of 2 settings, either shared or exclusive. When it's shared, a data reader sees updates from all data writers for an instance. So if you have the 2 things publishing data for the same satellite, the data reader would see samples from both. When it's set to exclusive, then the data reader only sees updates from one data writer, and it kind of picks who is the, quote, owner of that instance. So the way it picks is there's another QoS policy called the ownership strength, which is set on the writer side, which says, this is my strength writing this sample, this instance, and the one with the highest strength is declared the winner. So that allows the service to select the correct source of data for that particular instance. So coupled with that is another policy called liveliness. You would think liveliness goes kind of in the timing bucket, but it's really used in the redundancy part, the redundancy capabilities, where it specifies a mandatory interval for a data writer. So if this interval elapses with no activity, like it doesn't write a sample or it doesn't at least signal that it's still alive, then the data reader can receive an event, and or the ownership of instances might transfer. You would use liveliness, perhaps it went offline, perhaps the network got disconnected, et cetera. You would want to switch over, fail over to a new writer for that instance. There's 3 categories here, 3 kinds. Automatic, the service is automatically going to signal liveliness. So if the application doesn't do anything, the service knows it's still running, it will produce a heartbeat for you. Manual by participant, the user in this case is going to have to manually say that I'm alive, and that's going to apply for all the data writers in that participant. And then manual by topic, the user again is going to have to manually do it, but it's specified in particular data writer. You can use liveliness without using exclusive for the ownership if you just want to detect if the other side's alive and make some kind of decision based on that. So that is useful in itself. So the logic for actually determining who the owner of an instance is again, a data writer is going to take ownership when it writes that instance with the highest strength. It's going to lose it if it changes its strength to not be the highest, i.e. there's another one that's now writing higher. It becomes not alive because of liveliness, or it missed a deadline via the deadline QoS. So one of the gotchas here is that breaking ties in ownership strength is implementation dependent. So the application, you should really engineer it so that there are no ties. That way that you're not relying on the implementation to perhaps do something that you might not agree with. For shared, there's another policy that's relevant called destination order. So if multiple data writers writing the same instance, we need to logically make sense of that. So one way of doing that is ordering them by the time that you receive it. In this case, as data is received, it's presented just in that order, and that's the order that the reader sees. The other alternative is to order it by the source timestamp. So the data writers stamp the data with a source timestamp, and then you would order data that way. If you get data out of order, you're then going to discard some of the older data as it doesn't make sense temporally anymore. And this QoS kind of assumes that your data writers' clocks are synchronized enough to where that ordering problem is not going to be persistent in any way. Transport concerns are, there's 3 here. The reliability QoS is probably the most important one of all the QoSs, honestly. And that determines if samples are resent. So there's 2 kinds of reliability best effort. If and you should use data best effort if the data writer writes frequently and drop samples are okay. So if it's going to just continually write samples and if you drop a couple, it doesn't matter. Use best effort. Otherwise, you should use reliable. One of the gotchas here is that the default is reliable for data writers, but best effort for data readers. So everyone that I've ever known who's written a DDS application at one time or another has been bitten by this, where they ask, well, why am I not receiving data? Oh, because I didn't set reliability on my data reader. So I don't know why the spec writers did that, but it is a gotcha which seems to trip everybody up at one point. Another QoS in this domain of just transporting data is transport priority. So this is just a hint about the relative importance, and an implementation could use that to like change a thread priority or network priority if your network supports it, etc. It's implementation dependent and not interoperable. So it would just be depending on whether or not you get support for it. Latency budget QoS is a local hint about the time allowed between a write and when the sample is available to the data reader. So for instance, if you say, this is really high latency data, you can take 10 seconds to move it from the writer to the reader, then the service can say, well, I can do a lot of different stuff in that 10 seconds. I may be able to prioritize something that's more important and then get to this later. So you could advantageously delay samples or spread data out to avoid burstiness in the network, something like that. So again, that's just a local hint that's implementation dependent. The last kind of category that we're going to look at is resource limits. So resource limits sets limits for the samples maintained by the service. One is max samples, which is the total number of samples in a data writer. Max instances is the total number of instances, and then max samples per instance is really given by its name. That's how many samples you can have per instance. And you'll use these in, they're obviously appeal to resource constrained environments, but there's other uses for them well, just to manage how much data that you have and you want to deal with. The next QoS is entity factory QoS. Controls if an entity is enabled when it's created. It doesn't get used very much, at least in what I've seen, but it's useful if you need to configure something after you construct it without enabling it yet. So that's why you would use that QoS. The next one in the resource management kind of bucket is writer data lifecycle. So this is controls if the service automatically disposes instances when unregistered. So if you have multiple data writers writing the same instance and you want that instance and data to kind of survive one data writer going down, then you should set this to false. That means that the data writers would have to explicitly dispose, which means to delete that data out of the system. This is kind of a very subtle thing, but it definitely has its uses when you consider multiple data writers for the same instance. The next one, if there's a writer data lifecycle, there's a reader as well. So the reader data lifecycle allows the service to clean up samples and instances that are basically dead. So if you get to a point where there's no writers for that instance anymore, those can expire after a certain amount of time, similar if they're disposed. This is usually in the case where you're not taking samples out of the data reader. So a take kind of destructively reads it. It takes it out of the data reader cache to where the data reader doesn't have to manage that sample anymore. If you're just reading, then there's a chance that these things can accumulate over time and lead to a resource leak, which is kind of what the slide was about. So one of the gotchas here is that the built-in topics are set up this way. So if you do not change the built-in topics, you do not take from the built-in topics, you can get a resource leak by just the churn of entities appearing and disappearing on the network. Okay, so I know that was a whirlwind tour. I know that was a whole lot of stuff. But what I hope impressed you was that QoS is really fundamental to DDS. It wasn't an afterthought. It was a conscious thing that was put into the DDS spec. And really, to be effective with DDS, you need to understand QoS. It gives you all of these tools for working and designing distributed systems, implementing distributed systems that really prevent you from writing a lot of code at the end of the day. So the various QoS policies make DDS a great choice for distributed systems because the policies are designed really to solve recurring real-world problems in distributed systems. So with that, I think we will open it up to questions.
So Justin, question number 1 is, are all of these QoSs in DDS universe?
These are the QoSs in the DDS spec, but there are additional specs that define their own QoSs. So for example, X types, one, you can define what encodings are acceptable for a data reader. So the data writer specifies how it encodes the sample. The data reader can say, these are a list of acceptable encodings. And then if those things match, then the data writer and data reader will communicate. So each spec may introduce some new QoSs, QoS policies that are relevant to its particular function or configuration. So there are additional ones, but these are the ones in the main DDS spec.
Wonderful. Okay. So maybe this is a personal question, but what is your favorite QoS?
My favorite QoS is partition. And the reason it's my favorite is because it speaks directly to scalability and ease of configuration, if you will. So you can do wild things like you could have a partition based on your zip code, right? In which case you could now write applications that are geographically aware. You can treat a QoS string as like a hierarchical organization to where you can subscribe to different levels in a hierarchy of data. So partition just allows you to slice and dice your domain in so many different ways that it's really cool to me.
Awesome. Okay, and I think this is our last one, unless we get some more people asking questions right now, is what tools exist for working with QoS?
So for QoS, there's actually a spec, the DDS XML and JSON spec is one that allows you to kind of type up the QoS in a text file, and then the service can read those text files to configure the various entities. That's one tool. Your support for that depends on your implementation, but that's one of them. The built-in topics obviously present the QoS. The QoS themselves are defined in IDL, which means you can describe their values in different languages, and also with suitable code, you can like dump the QoS into a text file so you can see it for debugging purposes. And then finally, various tools, design tools, are going to allow you to do simulations with different QoS parameters. I'm not necessarily familiar with those tools, but I do know that they exist.
Awesome. Okay, thank you, Justin. So I want to thank all of you for joining us today. Please visit the DDS Foundation website for more information about DDS and to see some of our previous webinars. So thank you, everyone, and thank you, Justin. I hope to see you all at our next webinar. Have a good day, everybody.